Hi, this is Jose Luis, and welcome to another video on this series, Introduction to Parametric Modeling. In this video, I would like to talk conceptually and with a few simple examples about the notion of randomness. And I would like to address that because randomness is actually a technique that is fairly common used when doing when doing modeling in general. And I would even go farther to say that sometimes it's even a little abused in my honest opinion, but it's nonetheless a really useful technique. And it is useful because many of the things that we model very often are somehow inspired by nature. And it turns out that nature, for us humans, has a lot of apparent randomness. Things are not ordered perfectly on a grid. They don't look so mechanical, so orderly. And that's why we feel that very often randomness is a technique that leads us to things that are a bit more nature looking or more nature inspired, if you will. At the same time, randomness had like a sort of stylistic period where random facets or like random distribution of colors, whatever, was a thing just to like spice things up and stylistically, if you will. I don't really know why that happened, but it had its moment. Maybe people are still using it and it has like some real world utility. And that's why I would like to talk about this conceptually and discuss how computationally randomness is typically generated, handled, and a few things that we need to keep in mind that are important when generating randomness. And for us, computationally, when I say generating randomness, what I basically mean is generating sequences of numbers, because at the end of the day, most of what we do in computational design is represented by numbers. So when we want to generate randomness, what we need to do is we need to generate sequences of random numbers that then we use for specific purposes. How can we do that, for example, in Grasshopper? Well, if we go to sets and if we go to the sequence tab, you can see that we have a lot of components that we haven't really taken a look at, but I really encourage you to check them out. One of them being the random component, which generates a list of pseudo random numbers. I will address what that pseudo means very soon. And if we look at the icon, you can see that the icon is this kind of cat inside of a box. Are you nerdy enough that you know what that is a reference for? I'm not sure if you do, but that is a reference to Schrodinger's cat, or this metaphor that Schrödinger? Was Schrödinger or was it Feynman who did the metaphor? A metaphor about the duality of quantum states. That I'm actually not. I'm actually not qualified to actually explain that. I'm going to make a bad job. So just Google that. The Schrödinger's cat. Okay. Now, but the long story short was that the metaphor was about a cat that was inside of a box, and that while it was inside of the box, could be both at the same time alive and dead. But then when you open the box, then you randomly discovered whether if it was alive or not. But again, don't ask me why. Don't ask me why that is. Actually, I cannot explain that very well. So, but how do we use this component? Well, very simple. This component allows us to generate pseudo random numbers with a few particular inputs. For example, the first one is the domain of the range of numbers that we want to generate. So for example, I want to generate numbers from 0 to 1 with a domain. I also can select how many random values I want to generate. So for example, I'm going to generate 10 random numbers, and then I would like to be able to control the seed of the random engine. Let's put a pin on that one. Let's not care about that for the time being. But you can see that if I generate this, I generate a list of numbers that look random to me from 0 to 1. And if I expand this increment, you can see that the domain of this numbers generation expands proportionally. So before I had a range from 0 to 1, you can see that 77, 40, 16, and if I multiply the domain by 100, I still get 77, 40, 16, etc., etc. So you can see that this particular component, basically the domain, makes the range of those random numbers proportionally. How is this useful? Well, it's actually super useful because we can generate now, for example, sequences of numbers that we can use to, for example, create a collection of random points. Let me show you how that is done. So for example, I have my first sequence of random points, random numbers that I have generated from 0 to 10, and this is going to be 10 actual numbers. And then I'm just going to copy paste this whole thing and then paste it somewhere here to generate a second sequence of numbers. That is also going to go from 0 to 10. Then because I want to generate the same amount of points, I'm going to use the same slider here. And then I have my sequence of random points, of random numbers here. If I now construct a point using this set of numbers as the x coordinates and this other set of number as the y coordinate, I should get some randomly distributed points in x and y. However, I can see that there is some randomness, but obviously this doesn't look random because they're all aligned across this one diagonal. Why is that the case? Well, it turns out that if I look at the numerical values of the x coordinates and if I look at the numerical values of the y coordinates, turns out that they are exactly the same. And even if I vary the domain of one, yeah, the numbers change proportionally, but they stay aligned because they're still linearly proportional to each other. And whether if I add more or less, it doesn't really change. Well, I still have the diagonal. But wait, I have two different boxes. How come the two different boxes are generating the exact same amount of the exact same random numbers? I thought random numbers were random, right? Well, it turns out that the problem is that for these numbers, for both boxes, I am using the same default seed called number 2. And here also number 2. And if I were to change it with one and with the other, you can see that now I have random numbers here, and now I do have random numbers here, except for the moment where the seed is the same for both of them. What? But then, what is this concept of seed that you're talking about? Let's take a look at actually how random numbers are generated computationally. Let me start by some foundational notion about random numbers in computer science. It turns out that, as you can see on this meme, if you ever follow the Big Bang Theory, it's an amazing show. You should definitely check it out. It's very nerdy. And it turns out that it is true, as the meme says, true, real, random number generation using computers is a problem that still remains unsolved as of today for computers. Computers cannot really, for real, generate random numbers. And why is that the case? Well, think about it very, very conceptually. Computers are really good at computing things, aka taking some initial data, processing that data somehow, and churning out derived data. However, computers generating a random number conceptually means without any input data, without any reference, or without anything that is driving that generation, purely create a random number from scratch without no reference to anything before. If you think about it, that is probably one of the most creative processes that can be conceived, the generation of something out of absolutely nothing. And then that turns out to be computationally a huge problem. Such a huge problem that it hasn't still been solved today. And there's no prospect of that ever being solved. Because again, computers are really good at processing data based on some original data. They're really bad at generating stuff from absolutely nothing. That is, again, a very creative process if you think about it that way. So how do we then generate random numbers? Well, if we want to generate real, true random numbers, there are some techniques that are fairly modern, actually, that high specialized computation environments use. So for example, it's very common to use atmospheric noise as a way to drive the generation of random numbers. And actually, if you go to random.org, one of the most common tools online for generating random numbers, it uses atmospheric noise here. Just because there is like these sounds that are in the atmosphere that vary, that fluctuate, and it turns out that statistically they can be used to generate pseudo random numbers. Or for example, there's this company called Cloudflare in San Francisco that is very well known for having in their headquarters, having a wall of lava lamps like these ones with cameras pointed at them and then measuring how the lava moves up and down and then using that to generate random numbers that they use for cryptography service that they sell. Because they need a lot of random numbers to feed new cryptographic keys for their encryption services. So when you need like real true random numbers, you use things that are inspired somehow by nature, and you use that inspiration so that it cannot be predicted mathematically or with an algorithm. But for not so professional or not so, for more like, like daily use for simpler things that don't threaten anyone's security or bank's accounts, then there are actually simpler methods to use. It turns out that the generation of random numbers in computer science is typically done with a series of equations or a series of expressions that have been proven to generate sequences of numbers that statistically seem random. So, long story short, their random number generation can be done with expressions, so either equations or polynomials or ways of generating sequences of numbers that look, for example, something like this. That they take an initial value and then they start generating sequences by using a fairly complex expression, if you will, and then these equations have been proven to generate sequences that statistically are random because they have even distributions of outcomes across a domain, right? Now, one of the consequences of this process, one of the consequences that in order to generate random numbers computationally, we use algorithms, we use an expression that is fairly complicated, but it's an expression. First of all, that is very unsafe if we use that for cryptography or for security. That's why we have the lava lamp situation, because if somebody finds out what the algorithm for generating random numbers is, then you're basically screwed. But, but the other consequence is that the numbers that we generate with these expressions are pseudo-random. And they are pseudo-random because they always start by a given number that is typically called the seed. And then what they do is that they operate with that number over and over again, or with the derived numbers from that initial one. And it turns out that for any particular seed, so for any particular starting value in the calculation of random numbers, these expressions generate pseudo random numbers because for the same number, for the same seed, they will always generate the same sequence of random numbers. So if I give this particular expression, if I start with the seed of 0, I will always get this particular sequence of numbers. If I start with the value of 1 for the seed, I will get a different sequence of numbers. But if I go back to a seed of 0, I will get the original same sequence of numbers as before. Because again, these sequences rely on some input, which is typically the seed, and then they manipulate that seed in order to generate sequences of numbers. So if they always start from the same seed, they always will generate the same sequence of numbers. So that idea that there is a seed or a one initial number that drives the generation of the random numbers is paramount to the way we generate random numbers, because what it means is that random number generation is deterministic. And when I say deterministic, I mean that it can be predicted based on the seed number, if we know the seed number, and if we know the algorithm, then we will be able to actually generate the numbers ourselves. So for the same seed, we will always be generating the same sequence of random numbers. And because we were using the defaults here in Grasshopper, that's why we were getting the exact same numbers for this box and this box, because these are not looking at the atmosphere or any lava lamp. And therefore, the only thing that I need to do is I need to give each one of the random number generators a different seed. And with a different seed, I will generate different sequences for the x coordinates and different sequences for the y coordinates. And now we have something that looks way more like a random distribution of points in a two-dimensional space. I can extend this same idea to 3 dimensions by just copy and pasting this guy here. I still have the domain, I still have the same number of numbers, but I use this as the C value, and you can see how they're all in a plane now because I'm using the same seed value for Y and for Z. But if I now change the seed, you can see how the points are now evenly distributed, or like randomly distributed in a box that is 10 by 10 by 10. Let me actually draw that box from a domain, and I have the domain here, the other domain here, and the other domain here. But I have the points, and these points are now randomly distributed inside of this box. And if I place some spheres in here, then I can see the points. The spheres. I can see the sphere. Oh, that is not. I can see the spheres a little more. Well, I cannot see the spheres. So no spheres. I like this better, like this. Okay. All right. What else do we need to talk about the random numbers? Sometimes if you look at the random number generation, you can see that in the case of Grasshopper, and this is specific to Grasshopper, the way we have generated the numbers here, these numbers do have all decimal part. And then it will be very often the case that we will want to generate integers that are also random. So how can we do that? Well, you might feel inclined to say, all right, let me copy all of this, and then I'm going to generate like, I'm going to generate all these random numbers here. And then in order to figure out how many numbers do I have here, in order to generate integers here, what I'm going to do is that I'm going to just round these numbers up. Okay, so for example, I can go to math, and I can go to I forget what it is. Is it here polynomials? No, I think it's here is rounding. Yes. So in utilities, you have a component that rounds numbers, and then rounds numbers, and it gives you n, the integer that is nearest to x, then the floor, and then the ceiling. So if I take n, you can see that I can have here 7, 8, blah, 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 whatever, which looks okay. It looks randomish. However, make sure that you never do this because, for example, let me show you what would happen if we generated. So let me show you first a way of figuring out how many elements do we have in here. So if I want to know how many zeros, how many ones, how many twos, how many threes I have in this random list, a technique that I can use is I can go to another tab that we haven't seen yet. So in sets, I can go to sets. And then here, what I can do is I can take a look at the member index. So that, is it member index? Let me double check this. Yes, it is member index because this component tells me the amount of times a specific member is found in a set. So I'm going to drop this here, and I'm going to say, well, in this one, in this list of numbers, how many, this is the set that I want to figure out, how many, I need to also give it the members that I want to search for. So I'm going to generate a series of numbers that is going to go from 0 to the number 10. Okay, so that I need to give it 11 elements so that it goes from 0 to 10. And then if I fit that in, you can see that what I need to do is I need to make sure that I first convert these numbers that have decimal part. I need to convert them to an integer. And then as I do that, you can see that what I get in result is a tree that tells me, oh, this is nasty. The number of occurrences of the member. Sorry, this one, yes. The number of occurrences of each one of the members. So you can see that this list has apparently, for example, it has the number 0 is not present. Number 1 is not present. Number 2 is 1 time. Yes. Number 8 is 2 times. So here and here. Number 6 is also 2 times. Here and here. So with this, we can check how many elements are present in this random distribution. So one of the things about random distributions is that they are designed in a way that the numbers are sort of evenly distributed when it comes to really large amount of these values. So if I were to generate a 1 million points, for example, is that 1 million? Yes. If I were to generate 1 million numbers, I would expect that the distribution of these numbers, of how many zeros, ones, twos, threes, whatever, would be more or less the same. But if I do that, let me just crank this all the way up to 1 million. First of all, you see how my computer is frozen a little bit and it has taken quite a couple seconds to do. Then look at what is happening here. The random number distribution is kind of good because you can see that the number 1, 2, 3, 4, 5, 6, 7 roughly have the same amount of occurrences. So you have roughly the same amount of chances to get the number 0, 1, 2, 3, 4, 5, and 9. However, you see that number 0 and number 1 are roughly half. They are roughly half because when I was rounding these numbers, I was rounding to the nearest integer, which means that let me do this in a diagram. If we say that we're generating random numbers between 0 and 4, for example, and we generate them at random intervals, if the rule that we use is rounding to the next integer, then basically what happens is that all these numbers that are here, all of these are going to round to number 1, all of these are going to round to number 2, all of these are going to round to number 3, but because there's no negative numbers or there's no numbers over 4, you can see that the amount of numbers that get rounded to 0 and to 4 is kind of half, because there's just only half, there's only half space in order to place those numbers. So that's why, for example, what it's typically done here is that instead of rounding numbers to the nearest integer, which is the regular way of rounding numbers, when we typically generate random numbers that are integers, when we round them, we use the floor rounding. And floor, what basically means is that no matter the decimal part, we're going to round to the lowest integer smaller than or equal than x. What that means is that if I go back to the diagram, now my diagram, instead of looking like that, it looks like this. All these numbers are going to be rounded to 0, which is the lowest integer. All these numbers are going to be rounded to 1. All these ones are going to be rounded to 2. And all these ones are going to be rounded to 3, which is the natural way of rounding. And each one of them will be more evenly distributed. So let's see if that is true. If I change this and I use the floor instead of the natural number, you can see that now we are at a more even distribution, but also check what has happened. Now we know that we don't have any elements rounded down to the number 10, because if 10 was the upper limit, then there's no possible rounding down to that number. Wait, but what if I mean, these are random numbers. Is there a possibility that we would ever actually get the exact value of 4? Would it be ever possible to get the exact value of 4 and therefore this gets rounded down to floor? Is that a possibility? Well, technically it could be, because this is random numbers. You have equal chance of hitting a real number than not. Really? Well, that's not actually true. Don't quote me on that one. But technically you can. So it turns out that most random number generators that I know, what they do is that they ensure you that they can generate numbers for a given range. They can generate numbers that go from the initial value that you give them included. So they can generate a 0 in this case, but they generate numbers all the way up to the upper bound excluded. So they guarantee that you will never get a number 4. And that is represented with this inclusive square bracket. That means that 0 is included in the domain. And this parenthesis means that 4 is excluded, that will never be part of the random number generation. And the reason for that is what you just saw here. The idea that you can use this to generate random integers with an equal distribution. And therefore, when you want to generate random integers, you need to generate numbers from 0 to the upper bound of the integer that you want to generate without being included. So if I want to generate random numbers from 0 to 9, my domain has to be from 0 to 10, because we know that 10 will actually never be included. Okay? This part, this integer thing, was a little bit perhaps more advanced, but keep it in mind, because you will run into this issue at some point in the future if you keep doing these things professionally or for fun or in your design life. I don't know. All right, so I think this is more than enough for a crash course on random numbers. Remember, random numbers can be generated very easily computationally, but they will always be pseudo numbers, at least within programming languages and without using external services that look at the clouds and the lava lamps. So there will always be pseudo random. They will always depend on a seed. And for the same seed, they will always generate the same series of numbers. And also this whole ordeal of generating integers and rounding down, which we already heard me. So we're good with that. Now shall we do a few hands-on exercises to see how can we tame and how can we control randomness for our advantage? Let's do a few of these, because this is going to be a super interesting topic. And like this video, subscribe to the channel. Maybe if you like it. If you don't, then just move on. Maybe don't dislike the video, but if you don't like it, just move on your life and forget about me and all those things. Okay, thank you very much. See you on the next video.